a cascode amplifier or cascode stage. Okay. Now it's a combination of two type of amplifiers, okay, or two type of stages. So what are they? For a cascode, how will I build a cascode amplifier? I think you would have learned in AMC. Okay, so it's nothing but it's a combination of a CS amplifier with a common gate amplifier. Yeah. So I forgot one more thing. Now I wrote down this gain expression for this common gate, but what about the R in value of these common gate? Yeah, it's a finite value. It is not equal to infinity. So because of that property, can I use that as a voltage amplifier? Even though I have got an expression of gain that is closer to the gain expression of CS amplifier or CS with source degeneration, can I use this as a voltage amplifier? No. Why? Because of the low input impedance. So what type of amplifier I can use for it? No. Current gain amplifier, right? Because for a current gain amplifier, the requirement is that the input resistance is supposed to be as small as possible, such that you can draw all the current into the circuit to amplify it. Okay. Whereas in the case of a voltage amplifier, the input resistance has to be high enough, okay, such that we are not dropping the voltage of the source itself. Clear? So because of which we can visualize this the common gate amplifier as a current gain amplifier. Okay. Yeah, that's the small introductory part. Okay, so I will not discuss much about it. Yeah, so from this case, we could able to see that the combination of the CS and the CG amplifier could then build as what is known as a cascode amplifier. So let us try to build that. So I'll just begin with a resistive load, and later we'll just talk about replacing that load with some other structures. Okay, so I'll have a load RD and then a V out. Now at the bottom, I need two structures, okay, which have been combined, and they have been connected basically like this. Now in the top structure, I have to place a common gate amplifier, and at the bottom structure I have to place a common source amplifier. Okay, so let us plug in those things. So the VB is fixed to a constant potential, the gate potential of my M2 transistor is fixed to a constant potential VB, and whereas the gate potential of my M1 is connected to my Vin. Okay, so that is how I have this structures. Now let us try to jump into certain approximation. I will also call this node, the node that I have here, as X. Okay, so just for our reference, so we'll just talk about those nodes variation with respect to the input, and later we'll discuss about the drawbacks of this particular circuit. Okay, so first what I do is that let us try evaluating the gain of this particular circuit, and then we'll move on to the large signal analysis in order to read out the output swing. Okay, yeah. So now the whole point is that the circuit becomes complicated just because I've tried to cascade two different stages. Okay, now in order to ease our problem, what we do is that let us assume that the R0 of both the transistors are basically infinity. Okay, which means that I'm going to assume that the lambdas are equal to 0. Okay, now under this condition, I just want to evaluate the capital GM. What would be the answer for that? I think it's a pretty straightforward. One way that I can visualize this entire thing is to go for G2. So obviously a VB potential would be grounded here. I have this source terminal of M2, so I'll just put it as S2 here, and the source is connected to the drain of my M1, so I just write it as D1. I have this source being connected to ground, and across G1 I have this Vin, small signal Vin. Okay, and obviously for reasons I can drop the resistance RD. Okay, just because I'm trying to compute only the GM. So in that case, I'll just drop this guy, and I just looking for this I out. Okay, so if you could be able to find the relation of this I out with respect to the input, then my GM computation is done. Okay, now let us try to put in all those variables that we know. Now, whenever there is a value of of VGS with the polarity of plus and minus across the gate and the source, then we know that there is a current that flows between the drain and the sourse, which is GM1 times that of VGS. Okay, and since because the value of lambda is taken as 0 in this case, we will not worry about this R0 over here. Okay, so what about this guy? How will I draw the current for this? Do I have VGS here? Yes, we have VGS. So let me mark this VGS2 with the same polarity. Okay, so later we'll just map those potentials with respect to whatever we have. But as of now, I'll just go with the same thing, and I can write this current as something like GM2 VGS2. Did I miss something? Yeah, body effect. Yeah. So we have something known as a body effect. So I would include that component as well, which is GMB2 VBS2. Okay, so this is what I have. Now, I think if I could able to get the relation of this VGS1 with respect to the Vin, my answer would be almost done, right? So what is the relation that they share between this VGS and the Vin? Same. Yeah. So VGS1 is basically equal to Vin itself, right? So what would be the I out here for the current drawn schematic? What is my I out? Yeah, it is just minus GM1 VGS. Okay, so my I out is just this current that could have been splitted across these two current sources, but doesn't matter. But what is coming out is this current that I have here that is related to my Vn. So due to which I can write I can express this I out as something like minus GM1 times that of VGS, and we know that the value of VGS is basically equal to Vn itself. So I have this, and because of that, the GM has become very simple. Okay, so this simplification happens only when I assume that the lambda equal to 0, but the same will not applicable when I go with R0. Okay, so again, at this graduate level, we will not go dealing with R0, but what we do is that we will try to add up some sort of difficulty in the evaluation of the GM. Okay, but most of the time we can deal with approximating the value of GM to GMN itself. Okay, so let me give a small exercise such that you get a feel out of this GM computation. Okay, is there any difficulty in computing the value of R out for this in this case? What is the R out of this? Because that would ultimately give us the gain expression, right? Yeah, but R0 is basically infinity, right? So we basically have an output impedance which is just RD, okay? That goes in parallel with an infinite impedance, so it is effectively just RD, okay? So now let us compute this. Yeah, so one of the trick that I'm going to use is that I have a resistance RP, okay? So now that you need to find GM, okay, so once you have this GM, I think computation of output impedance is pretty simple, okay? So what I've done here is that I've just included a resistance in the place of R0, that's it, okay? So we have to think what currents flows out, and then we have to come up with the answer. Okay, so I will also assume one more factor here, that my gamma is also considered to be equal to 0. Okay, so that will not mix up too many things. So what currents actually flows out? Say for example, I just want to bring this node to the ground, and I'm trying to expect an I out. Yeah. So what current? Okay, so basically the small signal current originates from which transistor? First of all, the initial current flows from M1, and what current is that? GM1 Vin1. Oh yeah, so VGS1. Okay, and that current actually sees two type of resistance in this path. Okay, you see one of the resistance is this RP, the other resistance is the resistance that I'm looking towards M2. Okay, now which current is flowing out? Basically the current that flows through M2 is the one that is getting outputted, right? So if I could be able to know what is the current that comes out here across this M2, then my solution is done. Okay, so basically what I'm trying to say is that I have this Vin and I have this source that is connected here. I have this VGS with this polarity, due to which I have this GM1 Vin, and there is an external resistance connected to the drain. And I'm looking for I out here. So with respect to this node drain of my M1, it sees that this current source basically sees two different branches. Okay, one of the branches is this, which is labeled as 1. There is also one more branch that it sees. Right? What is that current basically? Yeah, so it is something like 1 by Gm is the resistance that it sees. Am I right? Because lambda and gamma we took it as zeros. Okay, so I'll just consider the only this 1 by Gm2. Okay, now. And whatever the current that flows is obviously coming from this drain terminal of my M2 as well. Okay, so I can relate whatever that comes through this resistance is related to my I out as well. Okay, now how would we compute this I out? Yeah, so in the previous case we were been using this voltage division rule. Now that what I have to do is that I have to go for current division rule in order to compute what current flows through this 1 by Gm2 resistance. Okay, so how would you do that? What is the total current that I have here? Yeah, this is the total current that I have, and I just want to know what current flows and gets connected to my I out. Okay, and that is what I wanted to find. Okay, so I want to know what is this current ID2. So ID2 is nothing but my I out. Basically, I have to invert the signatures, or I'll just use this. Okay, and I will also invert the sign of this. Okay. Says that the current through this RP is adding up with this ID2 in order to create this total current. Okay, so that is what I'm trying to reflect here. Yeah, so now this current is nothing but the total current that I have here is ID1, which is a negative value, into which resistance I have to take into account for current division rule, 1 by Gm2 or RP? RP. Do you all believe, right? Yeah, network theory. So I cannot help out. So based on the network theory subjects that you have learned, it is basically you have to consider the opposite resistance. Okay, so which is RP divided by the sum of both the resistances. Okay, so which is RP plus 1 by Gm2. That's it. So that gives me the value of current that flows through this M2 transistor. Okay, and that is the current that is being taken out as a I out. Clear? This I'm just taken as just ID2. Okay, so we are not worried about how it is dependent on the value of VGS of M2. Okay, what is to be considered is the resistance seen across my source terminal. Okay, so that would help me to get the answer. Okay. Yeah, so in that case, my capital GM would then be returned as ID2 by Vn, which is GM1 GM2 RP divided by 1 plus GM2 times RP. Okay. So this is the capital GM that I have got. Okay. So any doubt, you can raise your hand so that I can just come and check, or if you are comfortable with this answer, we can just move ahead. In case if my gamma turns out to be a non-zero factor, the only thing that I have to modify in this expression is just including this GM2 prime. That's it. Okay, so nothing else. Yeah, so what about this R out? If one could visualize that this RP is basically seen from the drain of this M2, what happens to this resistance? Magnifies, diminish, which is right? No, diminish. I'm looking through the drain. Yeah, it gets magnified by the intrinsic quantity, and the intrinsic quantity is nothing but it's a product of Gm into R naught. But what is the R naught of this M2 transistor when I have lambda equal to 0? Infinity, right? So whatever the resistance that I see at the bottom is basically infinity. That goes in parallel with RD. So effectively the resistance is just RD itself. Okay. Okay. So the multiplication of this Gm and R out should get you the answer for it. Let us move on to the next one, where we will try to relieve this lambda factor make it as a non-zero, but I don't want to make you to think so much, so I'll just make the load an ideal one. Okay, so what I really mean is, okay, so now in this case, I've just removed those constraint that I had before of having this lambda equal to 0. Okay, so I've just made this lambda not equal to 0 right now, and because of that, R naught, yeah, is no more infinity. So how would we compute this GM? But output impedance is, I think it is pretty easier for us to compute. But the point is that, what about this GM? That is where the let me start with the discussion of Cascode amplifier. We have already started the discussion in the class, but what I did is, when I went on to large signal analysis, we had certain discussions. So I thought I will just redefine the discussion again. And later, once this is done, once I make sure that it is clear to you, then we will just try to do a problem on it. Okay. So, Cascode amplifier. Now we know that this cascode amplifier is nothing but it's a two-stage, it's a combination of two stages with this CS amplifier along with the common gate amplifier, right? So I'll just quickly draw the circuit of it. Now let me first define a few of the terms here, or basically I just want to work out the Q point, and then later let me define the swing around those Q points. And once we are comfortable with those definitions, we'll just get into a problem. Okay, yeah. So first let me define the Q point at this particular node. So let me call this node as X. Okay, so when I refer X, I'm trying to talk about this node, and I just want to define the Q point of this. Okay, so before that, let us try to evaluate the Q point of this node V out. Okay, so at output node, the Q point is defined as VDD minus the drop across the resistance, right? So I have something like VDD minus ID times RD. Okay, now one has to imagine that the value of this ID is basically defined by the bottom transistor. It's always. So how it defined is basically there's supposed to be a fixed DC VGSQ, right? So this fixed value of DGSQ would define a current ID, and that current has to flow right through the resistance, through M2, through my M1 to the ground. Okay, so it starts from VDD to all the way to the ground. Hope that it makes sense. Okay, now let me write that. So basically the ID is defined by the VGSQ of M1 transistor. Okay, so hope that it is clear. Yeah, so now having said that, this current that flows through M1 also has to flow across my M2 transistor as well. So now if you want to have that particular current to flow, then it also has to have a particular value of VGS in order to make this current ID to flow across this M2. Okay, so if you are not having the enough value of VGS across this, then obviously the current cannot be equal to the current that has been defined by this M1. Okay, now let us try to define the Q point at node X. So Vx of Q, how will we define this particular node? Because we had a long discussion in the class looking for different way of expressing this. Okay, so for first what I do is that I will just try to address in a wrong way, and then later I will try to correct myself, stating why not exactly the right way. Let me begin with the way that you people thought in the class. Okay, so some set of people had discussed that the value of this Q point that I have here is supposed to be equal to my VOE1. Okay, so there was the discussion. Okay, so now this cannot happen for reasons I will just tell later. But one thing that I can state is that what is the right way of expressing this node voltage is, rather than writing it as VOE, I can write it as VDS1. Okay, so this is an obvious definition. But how does this VOE1 definition is different from the value of VDS1 that I've defined here? So basically, the VOE1 defines only the minimum value that I need to have across the drain to source. Okay, so what I'm trying to say is that rather than expressing the VDS value with the minimum value, I can make use of the definition that whenever my VDS1 is greater than or equal to VOE1, I say that my transistor is in saturation. Okay, so now rather than writing it in terms of VOE1, I can always fix it to a value of VDS1 because it can take any value. Okay, not just equal to VOE1, and that's the reason why I just choose or prefer this definition rather than this definition for the value of Q point at this particular node X. Okay, so the other way, so this is one of the way some people were discussing with me. The other way to define is that since I know the VDSQ here, is it not possible for us to define the Q point at node X based on the VOE of this M2 transistor? Now the statement is this. Okay, I will express this. So since I know V out Q, I subtract the minimum drop across the drain to source as VOV2. So the reason why this is non-correct, or this particular expression is non-correct, is by looking at the graph. Okay, so let me draw two graphs. One is ID versus VDS. The other one is ID versus VGS. Now we know that for a given value of VGS, there is obviously a current, and this current is almost constant the moment I enter into the saturation regime. Okay. Now, as you could be able to see, the transistor that supports this current value, let us take that as I. Okay. In order to support this current I, the transistor M1 or M2 can have a range of values here. Okay. It is not just this VOV1 that I have to have across this VDS1, or VOV2 that I have to have across this VDS2, right? So it can support any range right from this end to all the way to a maximum value. We are not worried about this maximum, right? So there is a range of value. So there is not a particular value that fits the requirement of having a value of I to a fixed value or to a single value of VDS. Okay, there is a range that exists for the value of VDS for a given current I to flow across my M1 or across my M2 transistors. Yeah, but when I look for the same similar argument in terms of a different graph where I try to plot ID versus VGS, you could be able to see that there is a certain minimum value that I have to maintain, which is my VDH, and beyond which the current grows. Okay, like an exponential graph. Now in this case, if at all, if I need the same amount of current, the magnitude of this current on this, it is pretty clear that this current value would then intersect my graph only for a single value of VGS. Okay, so I need a single value, a particular value to define this particular current to flow across my transistor. So hope that you're clear. So what I'm trying to say is that in order to define the value of Vxq, I cannot use the VOVs or the VDS values or the voltage generally across my VDS to define my Q point, because those are the values that can change, or those are the values that has a range of values it can support. It is not a single value that it supports at a particular for a particular current. Okay, so in that case, I cannot use this or this expression to define my Q point at node X. Okay, but what I can use to define my Q point is one single particular value that defines the current through the device. Okay, not the range. So due to which I would remodify this definition of Q point at the node X with respect to this VB as VB minus VGS2. Now again, this VGS2 is a single value that has to be defined in order to make the current ID to flow through the device. Okay, so it's a single value. It's not like a range of value that we had. Yeah. Now, having said that, let us try to define this guy. Okay, so hope that you are clear with this. I have a Q point here, and that Q point is basically defined by this quantity. Now, what is this VB, or what value basically it has to have in order to satisfy the whole conditions? Okay, such that both my M1 and M2 are in the saturation regime. Okay, so based on this, you could be able to see that VB is a particular potential that I have right from the gate of this empty transistor towards the ground potential. So basically, a VB is written as plus and minus with respect to the gate and the ground. Okay, and obviously you could be able to see that this VB has to split across two components. One of the component is this VGS2, and the other component is nothing but the drain to source of M1 transistor. Okay, the value of this Q is nothing but our VDS1 itself. Okay, but what I said is that this cannot be fixed to a single value of VOE1. Okay, so let me define this as a drop across VGS2 as a summation of top across VGS2 plus the value of VDS1. So now with those basics, let us try to apply a small sinusoidal input and see what are the reactions that are happening across the node Vx and Vout. So let me add a small signal wiggle across this VGS1. So whenever there is a positive peak over this Q point that has been defined by the gate input, okay, what would happen is that it's a CS amplifier, right? So it's an inverting amplifier, due to which I will tend to have a negative swing here. Now, the question is that when I try to have a negative swing, I'm trying to lower the drain to source potential whenever I try to towards the negative cycle, right? So now what is this minimum value that I can have such that still my M1 stays in the saturation regime? The minimum value that I can have when I'm trying to lower the drain to source potential is nothing but our VOE1. Okay, just because whenever I try to go down, I'm actually trying to reduce the potential, trying to bring down the potential of this drain all the way towards the ground. Okay, but in order to make this M1 to stay in the saturation regime, I have to ensure that there is a minimum voltage across the drain to source which is equal to VOE1. Okay, that is what I'm trying to say. Now, the other way to think the same implication is that what happens is that when I try to have a positive peak across my input, I'm literally increasing the value of my VGS. Okay, so we know that the ID is basically a function of the VGS1. Now, what happens the moment I try to increase the value of VGS1 because of the positive peak? The current also has to be increased. Now, if at all, if my M2 transistor has to support the same increase in the value of ID, then the only way that it can do is by changing its VGS2 value to a completely new value. That is, from the previous value of VGS2, I have to increase the value of VGS2 in order to support a larger current, just because of the same relation that I have wrote it here. Okay, so means that how will I increase the value of VGS2? Because we know that the gate potential is already fixed to a potential which is VB. Okay, but the source has no fixed potential, so it can lower. Okay, so in a way, it is trying to push this node X towards the ground in order to have enough room for its new value of VGS2 to get accommodated such that increase in the ID flows through this M2 transistor. So that is how this Vx potential from the Q point been pushed down. Okay, yeah. So having said that, let us look for the maximum swing. Okay, so now currently I'm just trying to work between the node Vin to the node Vx. Later I will bring out the discussion of the same with respect to Vin versus Vout. Okay, so let me restrict our discussion only between these 2 points. So whenever there is a negative swing, let me just use a red color. So whenever there is a negative swing, what is happening is that I'm trying to reduce this VGS value, and obviously the current would also get reduced. So when the current is basically getting reduced, obviously the VGS2 of this M2 transistor has to get modified such that my M2 transistor supports the same current that has been defined by this M1 transistor. Okay, so again, by making use of the same relation, since because the current has got reduced, I also have to reduce the VGS value in order to have the same impact, right? So which means that the value of this VGS has to get reduced, and the way that I can do is by pushing this node Q point to a higher value. Okay, so it can go all the way up. So whenever there is a negative swing, there is an inverting stage between this node, and that leads to a positive swing here. Now, how far this swing can go up? The moment as I increase the value of this positive peak across the node X, what is happening is that I'm trying to reduce the value of VGS2 here. Now, there is a minimum voltage that I need to have such that there is a certain amount of current that flows through this M2 circuit, right? So that minimum value is nothing but VTH. Okay, so this guy can go all the way to a maximum value of VB minus VTH, and the transistor M2 enters into cutoff. Okay, so that is the reason why I marked this particular position as the maximum swing that I can have across the node X. Okay, from the base value which is defined as VB minus VGS2. Okay, yeah. So now that we had a discussion for a swing that is happening across the input to the node X. Now let us carry on the same discussion for the same similar swing that I have across the input to the output node. Okay, and similarly we'll just try to recollect that the output Q point is basically defined by this quantity. Okay, now whenever there is a positive swing, there is the green shaded signal at the input. Obviously, it's an inverting stage. So because of this inverting stage, obviously I would end up having a negative swing, right? Yeah. So now what is this minimum value that I can have for this output to swing down? Okay. In order to compute that, I also really have to think what is the relation between the gate and the drain such that I am at the edge of saturation. So let us try to recollect that our VOE2 is equal to VDS2. So this is the minimum value that I have to have across the drain to source potential. Okay, and that value is basically my VOV2. So I'm just talking with respect to the potential difference across the drain and source. I'm not referring the potential with respect to the ground. Please make a note of that. So in that particular condition, I would try to expand this VOV in terms of VGS2 minus VT2. Now again what I do is that one could actually remove the source potential. Just because we have a source and source, we could actually cancel out these two things, and we would have a relation between the gate and the drain to be defined as something like VD2 is nothing but is equal to VG2 minus VT2. Okay, because the source were common to both the VDS and the VGS, so one could actually cancel out both these terms. Okay, so and this is the relation that I have to satisfy between the drain of M2 to the gate of M2 such that I still at the edge of saturation. Okay, so with that definition, let us try to begin. So I'll just rewrite this expression, that is my VD2, which is nothing but my Vout. Okay, whenever I'm swinging down, how far it can step down is our question. Okay, and this is nothing but my Vout minimum. Okay, so VD2 is basically can have a minimum value which is defined by VG2 minus VT2. Now what is VG2? What is connected to our VG2? It is nothing but my VB potential. So I'll try to rewrite this in terms of VB. Now this is nothing but my VB minus VT2, and whenever there is a positive swing, we found that not only the Vout is stepping down in the negative direction, but also my Vx node is also stepping down. So when I am at the top of this particular positive swing, I'll be exactly at the most negative part of my Vout as well as the most negative part of my Vx node. Okay, and we know that the most negative part of this Vx node is nothing but my VOV1. Okay, so with those definitions, let me try to recollect. So this VB is currently equal to VGS2 plus the current value of VDS that I have is basically equal to VOV1. Hope that you are clear. Okay, so this VB2, which we have defined earlier as VGS2 plus VDS2, when I have a positive peak across my input. Okay, so when I'm at right away at this particular point, what is happening is that my VDS1 has to satisfy a minimum value. Sorry, this is not VDS1, sorry for that. It is basically VDS1. Okay, so I have to have a VDS1 with a bare minimum voltage which is supposed to be equal to VOV1. Am I right? Okay, so the minimum value that I have to still support when there is a positive peak across the drain to source of M1 is basically VOV1, and that is what I have plugged in when I'm talking about the positive swing across my input. Okay, so let me try to plug in this value as VGS2 plus VOV1 minus VTH2. Okay, so again one could see that the combination of this term and the combination of this term would give us a factor which is nothing but VOV2 plus VOV1, and that is nothing but my VO minimum. Okay, so whenever there is a negative swing around the output Q, I have to maintain a minimum voltage across the drain to source of M2 to be equal to VOV2, and the minimum voltage of M1 across the drain to source to be equal to VOV1. Okay, so if I try to go below this value, one among these two transistors would enter into linear region. Okay, now, so we have done with this positive swing for the input. So now let us try to talk about this maximum swing. So what is happening is that whenever there is a negative swing across the input, the output would rise up. Okay, and the maximum value that it can go up is basically equal to VDD. Okay, yeah, so I will not talk much about it because there is an interplay between this swing that I have here and the swing that I have here and the swing that I have here, and that is the major bottleneck. Okay, so I'll talk about this. Yeah, so this is my Cascode amplifier, and now that I just want to talk about the V out versus V in relation, let me try to plot V out versus V in graph. Okay, now whenever the value of this V in is less than the value of VT, we know that no current would flow through this entire circuit. Now, under this condition, what would be the value of this V out? We know that V out is generally defined as something like VDD minus ID times RD. And now that when I have a voltage across this VGS as less than VTH, we know that ID becomes equal to 0, and due to which the V out will have a value which is equal to VDD till I reach the value of V in that is equal to VTH, right? But what about the case here? No, we know that if at all, if I want to stop this current to flow through this M2, what's supposed to be the value of this VGS in order to ensure that no current is flowing across this M2? Now again, that's supposed to be equal to our VTH. Okay, so I have VB minus VTH as the value of Vx when the transistor is not drawing any current through it. Okay, so in this case, both my M1 as well as M2 are cut off. Okay, so what happens the moment I try to increase the value of V in above the value of VTH? Now obviously we know that the moment I start increasing the value of this V in, the current starts increasing, and due to which the V out would then step down. Okay, so one could normally draw this the kind of graph which we had earlier under the discussion of CS amplifier with a residual load. Okay, so I can use the same concept that we have discussed over there in order to plot this V out versus V in. But what about this graph? Now obviously when there is a current flow through the device M2, the value of VGS2 has to be expanded more than the value of this VTH. Okay, so in order to expand this value of VGS2, I have to lower the value of Vx down, right? So that's how I can have a value of VGS2 more than the value of VTH. So due to which this node Vx would then step down in a similar way that we had a step down for our V out. Okay, so we would have something like this. Now, as we know that once I cross a particular value of V in, one among these two transistors would enter into linear region. Okay, the reason is that when I try to rise up, the voltages across the drain of M1 or the voltage across the drain of M2 keeps stepping down. Okay, now let us assume that the drain of M1 is stepping down such that it doesn't have enough value of VOV, okay, across the drain to source. I'm just got a value of VDS that is less than the value of VOV1. In that case, my transistor M1 would enter into the linear region first. Okay, so and after a particular rise in the value of V in, since because even the drain of my M2 transistor is also stepping down, what happens is that at a particular value of VD2, the value would then become something like this, lower than the value of VG2 minus VT. Okay, so where VG2 is currently defined by the potential of VB, I've used that in that particular place. So whenever I satisfy, whenever I go below this particular value, whenever the drain goes below this particular VOE value, obviously my transistor M2 will also enter into saturation. The question is that who might enter into the linear region first? Okay, that purely depends on the value of VB that I use here, and the aspect ratios that I've used for M1 and M2 transistors. Okay, so it basically purely depends on these, as well as the current that is flowing through my device. Okay, now in order to understand, in order to boil down all these concepts that I have discussed, we have to work out an example to justify the statement that I have made right now. Okay, but obviously we know that both the device would enter into linear region for a particular value of V in, which is more than that. Okay, so let me define this as V in 1. Okay, so we don't know which one is entering into the linear region first and which one is entering afterwards, but let us assume that for a particular value of V in, one among these devices enter into linear region, and one could evaluate the swing, the maximum swings, just by looking at these V out versus V in graph, where I have both my M1 as well as my M2 staying in the saturation regime. Okay, so now even from this graph, one could actually tell what's supposed to be the value of VO max and VO minimum I can have, as well as Vx max and Vx minimum that I can have, right? Yeah. So now for which, first of all, I need to choose a Q point. Okay, so let me try to define the Q point such that it defines a particular value of current. Okay, so let me take this Q point as VGS1Q. So I have defined a value of VGS1Q here, and that defines a current ID. And in order to have that, I need a value of VGS, a particular value of VGS to be defined across this gate and source of my M2 transistor. Okay, so probably this. So now whatever I have here is nothing but the Q point VXQ, and that value is basically nothing but VB minus VGS2 here. Okay, and similarly, this intersect point will define the Q point at the output, which is defined as, so V out Q is nothing but VDD minus ID times RD. Yeah, so having this entire setup as a graph, let us look for the Vx variation. So the maximum voltage that the Vx node can vary across this base is defined as VB minus VDH, and the minimum value that it can have across this node is just the VOV1. So this point is nothing but my VOV1, okay, because it is the potential that I am talking across the drain and source, right? Yeah, so this is what I have whenever there is a swing around my Q point at the input. Okay, so this swing at the input creates a swing across my Vx, as well as it also creates a swing across this V out as well. So again, I'll just try to redraw the same thing. Let me use a red color in order to denote the change is happening across my V out alone. Okay, now whenever there is a negative swing, obviously it leads to a positive swing at the output, and that can go all the way to a topmost value, which is defined by this quantity, which is equal to VDD. Okay, and what is the minimum value that it can have such that my transistor is in saturation? So previously I have marked a particular point or a region, okay, where I stated that above this value, when the value of V in is above this value of V in 1, I said that both the transistors are out of saturation. So then what is this value that I have is nothing but the voltage difference between the drain and source of M2 plus the voltage difference between the drain and source of M1. So the voltage that I have to maintain across the drain and source of M2 is basically a minimum value of VOV2, and I think I'm just mixing up all these colors, so please do not get messed up. So the minimum value that I have to have is supposed to be equal to VOV2 across this VDS2, and this quantity is nothing but the minimum voltage that I have to maintain across the VDS1, which is VOV1. Okay, and it is just the summation of both these quantities that defines the lower minimum value that I can have across our output swing. Okay, so hope that you are clear with this, which is VOV1 plus VOV2.